Great. All right. Thanks, Faruk. So whenever you're ready. About the laser pointer?
Yes, I have it.
Oh, you got it. Okay, great. Thanks.
Okay, hello again, everyone. So I'm going to talk about layers, layerification, and all sorts of depth and layer related things. I think maybe this might be one of the important topics in a layer fMRI workshop, right? And just to prelude, because maybe there might be people who might watch the recording of this talk without my previous lecture, I work as a researcher and software engineer at Brain Innovation. I'm also affiliated with the Cognitive Neuroscience Department of Maastricht University. I currently work on mesoscopic cortical landscape analysis. You can see my latest paper here with some familiar names involved. I currently work on developing 3D fMRI analysis tools. This is really down to earth, like C algorithm development and implementation mostly. Then I disseminate expertise via walkthroughs and tutorials. So if you want like more details, practical aspects on how to do certain things, please have a look at that. I would like to acknowledge my collaborators. Dimo, Renzo, and Saskia helped me a lot with the acquisition and thinking about the high resolution data imaging. Rainer and Kendrick helped me about the analysis parts. And I would like to acknowledge specifically for this lecture, Konrad Wachstel, which we had a lot of discussions about layering. He's a histology expert. And special thanks to Daniel Glenn, Rick Reynolds, and Paul Taylor, because they give feedback on my lecture previously last week. Okay, layers, let's go. The true, real, actual, the real layers, or are we taking things too easy and thinking that there are easy categories that we can see and observe in nature and everything is easy and that's it? Or is it just some consensus, some social construct? Well, let's have a look at this figure from 1930 from Richard Arvet Pfeiffer. I redraw and translated this figure into English. This was in German. I mean, it's a bit small and you can feel free to use it later. But basically what this figure tells you that there are all these different researchers, von Economo, Maynard, Cahal, Bolton, etc. And they have their own layering classifications. And sometimes you'll see 6 layers. This is the visual cortex, by the way. Here it says diagram of the calcarine cortex at 50 times magnification. So 6 layers, 8, 9, 5, 8, 6, 9, 6. It's slightly different sub-regions. So you can see that it's actually not so straightforward to say, hey, cortex is just 6 layers, right? That's just some consensus that survived at the end and mostly built on the visual cortex. I am also like exaggerating the argument a little bit just for educational purposes. Of course, there are some parts, for instance, look at the layer 1. This is like very consistently labeled as a separate layer across researchers, right? However, for instance, one layer here, Hammarberg calls it in between layers. And maybe this reminds you the beach example from my previous lecture. Like where to put that boundary is uncertain in itself. And then you just decide, oh, I put it a bit here, a bit there. That's your decision. And maybe sometimes you just call it an in-between zone. I don't know where the boundary is, somewhere there. So this is just to remind you from John's first day lecture, which was very nice, about how people make use of these laminar areal boundaries in neuroscience. They basically stain tissues, highlight different components of these tissue compositions like cytoarchitecture, myeloarchitecture, or angioarchitecture, and they have a look at the cortex in detail. Wherever they see the pattern changing, I hope that you can see nicely here, they say, this might be an areal boundary. Maybe there's a different hardware in these 2 areas, and maybe these areas are doing different functions. This is the thinking. Myeloarchitecture and angioarchitecture, you can see, for instance, here, very dark, dense angioarchitectonic layer, and the white arrow drawn by Pfeiffer indicating maybe an angioarchitectonic areal difference between 2 areas. Okay, so looks fine, you know. Some people look at these images, they see differences, they put a boundary there. They say, hey, this is my area 1, that's my area 2, and so forth. So what's in our mind's eye is basically this image, which is, oh, it's easy. Like I take a chunk of the cortex, I look at it, there are layers, there are structures. So now I am going to make a bold claim. But actually, it's not so bold. This is completely oversimplified. Again, this goes back to the Plato's cave problem. It's like too easy to think of the brain layers like this. Oh, there's simple thing. It's like that everywhere in a certain area. There is no curvature. This is a good like exemplar of that region. No, we should completely forget about this. This gives like this starts us from the wrong footing to really comprehend the cortical layers. So now I'm going to elaborate on this, and hopefully you will see the other dimensions that we need to think through. And by the way, I am not claiming any sort of like some innovative new idea while saying this is oversimplified. Let's have a look at a nice book by Geyer and Turner, published in 2013. I will give a full reference at the end. And the chapter 2 written by Tiriarhu. And then there they show some old pictures where Konstantin von Economo and his colleagues explain the following case. They say that please do not cut the brain in these straight angles, because if you cut it like that, and if you look at your layers like that, the apparent thickness that you will see will not be the optimal thickness to see the laminar differences. You will be confounding the curvature effects because the cutting angle doesn't cut the cortex perpendicularly or in an optimal way. Therefore, they say, hey, this is our cutting method. And hopefully you can see in the image that there is this like wavy pattern, right? And if you really look at it and think about it, those cuts, those lines, try to optimize the cutting of the cortex so that you can see when you extract the slice, you can see the apparent thickness closer to the true thickness. And now you will not be confounded too much with the cortical curvature. And also, by the way, they shade some areas here to say that even if you use this optimized cutting angle, do not have a look at the cortical layers there in the shaded areas because they are the suboptimal cuts. They will make you confused about the change of layers. So this is nothing new. To think that, hey, think about the 3D structure, you know? Okay. So now, Konstantin von Economo, which I recently learned, actually, it was funny, like he was born in the Ottoman Empire as a Greek and then moved to Austria-Hungarian Empire later and become a baron. That was like, wow, then did all this stuff. So he draws the following diagram and says that, hey, look, when the curvature of the cortex changes, if it is sulcus versus dome, he has different classifications around the curvature. He says that, look, the layer 6 here, that is really thick, right? It becomes thin. And he says that do not confuse this with a different area, because this is just due to the curvature of the cortex, although he doesn't go beyond that. He just recognizes this and say, like, this is a confound. Anyone who do like architectonic parcellation should like take this into account and in his mind's eye and consider their aerial borders in the light of this fact. Then the next generation scientist comes, Siegfried Thomas Bock from the Netherlands, and he pushes this thought really further. And he says that there is actually a strong relationship between the relative thickness of the layers and the cortical curvature. And this is the part that we miss if we just think the cortical layers are those like bar-shaped diagrams, because there is no curvature drawn there. And he says that if I take more or less equally volumed chunks of the cortex, like this pizza slice in the gyrus, let's say this is white matter in the sulcus, he says that the amount of yellow here will be more or less equal to the amount of yellow there. So when you are bending the shape, you are kind of pushing the lower layers up and upper layers maybe thinner. if you think about it a bit, you will kind of see the idea, and I will try to make it more clear. But basically, Bock is the first person trying to like take this observation and try to derive a biological, physical law from it. Very important. So now, he talks about this stuff before World War II, and he had some trouble during World War II actually, because he's a part of a rebellion group I read during the World War II. So he struggled a bit, but in the later years of his life, in 1950s, he writes a book, and he translates all his publications that are published in German to English by himself in his later stage of his life. And he publishes a book. The book is called, and the title is very spicy. So I'm not the spicy one today. Bock is the spicy one. He calls his book Histonomy of the Cerebral Cortex. So I would like to ask all of you, have you heard this term, histonomy? No, right? Don't worry, I asked this to many professors. They never, none of them knew about this. Yeah, he made it up in 1959, right? And none of us are aware of it. And okay, what does he mean by this term? And you can really understand his point of view and how he was trying to change the way we do brain science and cortical parcellations if you read his chapter 1 and chapter 11. And this is just the contents of his book. And in the chapter 11, he titles his chapter Histonomy and Hypothesis. Wow, it's quite mouthful, I would say. And his whole point is that, I'm going to simplify, of course, he has a much more nuanced way of talking about it, and I really recommend you to go and read this book and read these chapters to understand his nuanced view. But basically, he says that what people were doing before was like astrology. Looking at these shapes and patterns, they see some patterns, they put lines there, they shapes there, they talk about it, this function, that function. Oh, if there are double peak, this will happen. But he said this is like astrology. We need to do astronomy, right? And he therefore suggests that I am not accepting histology anymore. I am actually starting a new field called histonomy, right? That puts the mathematics into the equation and not just looking at pretty pictures and think. I mean, of course, he also says that this is a part of the process. I'm now making it a bit more spicy for educational purposes. He says there has to be a back and forth between these two ways of doing science. Okay, so what is his core message in his first chapter, the second chapter, that is titled Curvature of the Cerebral Cortex? So his main message is the following. He thinks about the curvature. Okay, how does the brain curve and what would happen to the fabric of the curved cortex? He thinks, this is a redrawing from his picture that I made. So he starts from this 3x3 element, think that there are 9 cells there, whatever. Then you try to bend it. Well, you can make the size and shape constant or approximately constant, but then, for instance, here this upper part will have less number of elements. You can keep the size and arrangement constant, and that would mean that this part will be more triangular, more thickness will change, overall shape. Or he says you can make the shape and arrangement constant, so that this part will just become thicker. So imagine that cells just becoming thicker or thinner, right? Things like this. So he thinks about the curved cortex, of course, and then he uses his microscope. So what you see here on the top row is the cytoarchitecture pictures from a gyrus, a wall, and a sulcus. And let's say that this is a sulcus, this is a gyrus, and this is a wall, okay? He looks at a certain layer. So this is cytoarchitecture, this is myeloarchitecture. So he's investigating the shapes of the, in a way, fibers there as well. And what do you see here? Well, you see that when you look at the gyrus, you see more vertical shapes, right? Maybe not so clear, but you can really see it. If you look at the wall, for instance, myeloarchitecture looks randomly oriented. The cells look quite spherical and isotropic, nice. If you look at a sulcus, you feel that there is some sort of force, like pressing this material down and affecting their shape. They are like more vertical. And the fibers are also becoming more on the vertical shape. So therefore, he says that, oh, like this is one way of actually understanding what type of principle is at play. Really look at the shape of different constituents of the gray matter and how they change with different curvature. And again, going back to the beginning of the lecture, this is what we should always have in our mind's eye when we think of the cortical layers, especially in species like humans, where we have really curved brains, right? Maybe you are studying other species with not so much curvature, your time might be a bit easier. So like whenever we talk about cortical layers, we have to think about the curvature of the cortex. So, okay, what happens if someone ignores this principle? And he has a subsection about it, actually, a couple of pages written with some examples from the literature in his time. For instance, in the section called the erroneous supposition of architectonic sub-areas, this is his subtitle. He shows an example from a researcher called Rose, and he redraws his aerial parcellations. He makes a diagram out of it, and he highlights the following case. Look, the parts that Rose highlighted as an aerial difference, sub-areas in some like a certain cytoarchitectonic region. How suspicious it is that those sub-areas, delineations of these arrows, coincide with where the curvature is actually changing. You see that this could be, let's say, a sulcus, assuming that white matter is here. Sulcus, right, becomes more like a gyrus. It becomes a bit like a sulcus again, and so forth. And he says that this is suspicious. And he claims the following: maybe Rose delineated these subregions because he didn't know about the equivolume principle. So he was considering his data in the light of the wrong reference frame. That resulted him classifying, like putting arbitrary borders on the nature, right? But not using the right reference frame. And this might cause some confusion, of course. And maybe a bit more spicy take. Like, I don't know how much this issue plagues the current literature, to be honest. Considering all the animals, ferrets, like monkeys, humans, all the cytoarchitectonic, myeloarchitectonic parcellations, I really don't know, because I do not see enough people talking about the equivolume principle in the right way and using it in their calculations of cortical layers. So it might be that Bock's criticism that he made for the past 50 years of neuroscience in his era might still be true today. Or to a certain extent, let's say. Just to emphasize the importance of this principle. So now let's move to the intuition for the equivolume principle. So I made the following case. I think this is the easiest way for someone to understand. So let's imagine that we have a brain, and that's a ball brain, or circle brain, but the right is ball, saying ball. And let's imagine that white matter is an infinitesimally small pixel in the middle here, okay? And let's say gray matter is the whole of this thickness, and we have this ball brain. So now we computed layers there, easy, right? So-called equidistant layering approach. Or we say, oh, like I have 3 millimeter thickness of gray matter. I have 1 millimeter fMRI voxels. Surely I fit 3 voxels there to take 3 different layers, right? Okay. It looks correct. Now let's establish our bins using a different metric. That is the same shape, the same 2-dimensional toy brain, ball brain. And let's say that, hey, each layer should have this equal amount of area, not the distance from the white matter, okay? And if that's the case, this is the part where we struggle usually, because now, again, the Plato's cave problem, like this kind of feels natural and easy. And this, you look at it and you say, how can it be? Like the yellow in the middle is larger than the others, right? No, go there and count the pixels. They are the same area. However, now what happens is that just by having equal amount of material across these 3 layers, well, the deep one pushed the other ones up, right? So now it's not so straightforward anymore to say, oh, I have 1 millimeter layers and for each layer, I get one voxel fitted inside nicely. And now let's really escape from the plateau scale and think in true 3D form in this ball brain. And let's put the equivolume principle in action and say that I am going to delineate 3 regions where each voxel, like when I count the voxels in these 3 regions, they will have the same number, the same volume. And look how far your upper layers are pushed. Now you have 2 layers in one voxel, and actually, like, this goes back to something that a question came in a different context. That's this concept of relative resolution. Like, it's not so straightforward to say, oh, I have 3 millimeter thickness, I put 3 like voxels inside and get 3 layers. No, like, relative thickness of the layers changes with the curvature. So this is a big part, and we might also even maybe able to exploit this, which I will come back to. So basically here the point is that when you look at a 2D slice of a 3D object where the equivolume principle is in action, you might think that, hey, like, the upper layers are too thin. There is something wrong. Why is it so pushed like this, you know? Whereas you are not comprehending the effect, like the force of these being equal layers implemented in 3D. Truly, you are looking at it in 2D.
That's the volume whole sphere.
Yes, the whole ball. Yes. So like the light yellow here, just the light yellow, like you can think of it as a like empty inside, like a ball, is equal to the mid yellow and the dark yellow. And it is like this. Like, you can go ahead and make your own computations. So now let's leave the ideal world behind, the ball brain, and let's move towards the biological brain. So I think these 3 types of curvatures are the good ones to keep it in our mind's eye when we think of the human brain, or maybe dolphin brain, where we have a lot of curvature. So we have parts of the brain that is like not curved too much, and these are called, they can be called voles. These are maybe transition zones between sulcus and gyrus. We might have ridges where you have kind of one type of folding, but it's actually kind of a 2D structure because it doesn't bend in the other direction. And the third one, the most complicated and maybe most natural one, the saddle, where you have 2 types of curvature when you compute the curvature locally. There's some like simplification here, of course. And okay, now if we think of the equivolume principle, putting layers inside these geometric shapes, the equivolume principle, like, and also thinking of the biological tissue and what we really see in the walls versus ridges versus saddle, equivolume principle will work on all types of curvature. Equivolume computed layers will be equal to equidistant computed layers when you have a wall. That's an important point. But it will not be the case for the other way around, which is you are in a highly curved region. If you compute equidistant layers, you will be quite a bit off. So equivolume principle is the general solution to model the layering across curving cortex. There's a recent paper on it, actually published by a bunch of mechanical engineers and a few mathematicians. And please go ahead and have a look at this one. It's quite an interesting angle to think about cortical curvature. And they talk about things that we actually don't talk about too much, different types of curvature and how it affects the thickness and so forth. Okay. I'm trying to go a little bit slower than usual so that you can hopefully like think and ponder about these complicated 3D shapes and stuff. I mean, it's not the easiest, but you know, this is the first time I put this type of material together, and hopefully it will become like more and more honed in the future, easier to understand. Okay, so layerification. First, a couple of words. When Renzo told me this word 4 years ago, layerification, I hated it. I was like, this guy, you know, making new words again, like we have enough confusion anyway, like now we need to do layerification. How is it different than layering, making layers, computing cortical depths? I was complaining all the time. But after 3 years, I actually started seeing that he he is right. Maybe we should have a different word for how we use our computers and MRI data and our segmentations to generate layers. And maybe we should separate it from these biological layers, like cytoarchitectonic layers, right? That's So there is this biological layer, cytoarchitecture, myeloarchitecture, angioarchitecture. Most people refer to them as true layers, right? And I made a case that maybe there is not so much truth in it, but maybe a bit more consensus. But there's also another way we need to separate very carefully. That's the way we compute layers in a computer, right? And this is a very geometric way. Like we are not really looking at myelination or cytoarchitecture or anything. We have two surfaces segmented, free surfer, SPM, whatever, whatever software, two surfaces, and we try to put stuff in the middle. I think that we need to separate a bit ourselves from this like neurobiological layers, maybe one might say. And that I think I find the layerification term maybe a right one. Okay, so now let's clear up a couple of issues because this lecture is called Principles and Algorithms, and I have 75 minutes. I intend to use all of it, not 1 hour, just a highlight. I forgot to remind it to you. So what is cortical depth? What is cortical thickness? What is layers or maybe geometric layers, layerification? Now think of the following. This figure, by the way, is redrawn from Bock's book. He had this 3D nice shape. I just vectorized it, and I think it's quite useful to communicate some ideas. So what do we say here? Cortical depth is measured in millimeters, so physical distance units, and is relative to either white matter or outer gray matter surface. So I'm talking about these geometric ways of layering, right? I am now in the computer world, so don't think about site architecture or anything. I have two surfaces. I can compute. I take a voxel and I say, hey, how distant are you from the white matter border? Or how distant are you from the outer gray matter border, CSF, whatever. So that would be cortical depth, and that would be a measurement in millimeters, right? Or inches, whatever. But that's the point. There's a physical unit of distance. Cortical thickness requires two surfaces. Why? Well, think like a caliper that you put around like some wooden plank, maybe that measures like the distance between 2 points, right? That would be the thickness. It's the same, like we really need two surfaces to measure cortical thickness. So in a way, that's like a higher order measurement because cortical depth requires one surface, cortical thickness requires you to define two surfaces. So now let's have a look at these 3 points, 1, 2, 3. Let's first notice that the cortical thickness is varying, like general cortical thickness, right? I'm not talking about layers here. So it is 2.4 millimeters here, 1.2 millimeters here, 3.2 millimeters there. So it's varying. But this point that I have highlighted here, when you look at the ratio of its cortical depth to its cortical thickness, that ratio lies on the 25% of the local cortical thickness defined for those points, right? So this is a way of like summarizing these 3 different points and saying that, hey, they are at the same ... because they are all lying on the 25% of the local cortical thickness. And this is usually like in yesterday's dog's talk, the layers that he computes are these type of layers, like proportional layers, right? You say, hey, give me the 0 to 10% of the cortical depth. Give me the 10 to 20% of the cortical depth. But now you should notice something, some detail, which is we don't have physical units of measurement anymore. There is no millimeters. We divide millimeters by millimeters, cortical depth by thickness. So it became a ratio type of measurement, a fraction, right? Would you say depth to indicate fraction? Question mark? Okay, now let's think a little bit more on this. And here I say the word equivalence class, which is to indicate every point that lies on the 25% of the local cortical thickness. That's like a class of points, right? It can be infinitely thin, whatever, mathematically speaking. I think saying layer to indicate this equivalence class is not so wrong. I would even feel that it is more correct than saying cortical depth, because when you say cortical depth to a depth to a physicist, they would think, oh, like how many millimeters away is it, or how many kilometers away? How deep is this water, you know, or this corridor and so forth. Like there is no millimeters there. So maybe layer is not the wrongest term, but maybe we should indicate this is a geometric layer. This is a proportion-wise layer. This is a local cortical thickness normalized cortical depth layer. Okay, so ratios does not have units. Therefore, and I don't know actually if I make it worse by talking about it, but if one wants to be pedantic, you should really say normalized depths and maybe indicate how you normalize them, because you can normalize them in different ways. You can just consider cortical thickness, right? And that would be so-called equidistant layers, although some people would disagree. I actually had like physicist friends not understanding it, because they were, how can it be equidistant? Like it is 0.8 millimeters to one surface here, 0.3 millimeters to one surface there. Why do you call it equidistant? You know, call it equiproportion or something. Maybe, you know, maybe there's something, but I am fine with it because this is pretty well defined, fine. But that indicates the type of normalization that we apply, because we can also consider the curvature of the cortex together with the thickness. And that would result in a different type of metric that we would indicate this equivalence class. 25% of the equivolume normalized cortical depths, right? This would mean something different. That's more pedantic way of saying it. Therefore, I do think that like forcing the depth dependent to people who say just layers is the wrong way of going about it, and it is not pedantic at all. That's the wrong option. That's my opinion. If you really want to be pedantic, you can say, that's an option for you, curvature dependent, normalization dependent, depth dependent, dependent, right? Will be pretty hard to write. Maybe we should come up with another acronym, right? Hey, MRI physicists, time for you to shine. Okay, now the elephant in the room. I think we are all talking about it, but not really saying what it is and how to deal with it. I mean, John, of course, had an explanation this morning with response to the question. So let's define something called relative resolution, for God's sake. And why do we need it? Because imagine that I put a human inside my scanner. I did 0.8 millimeter isotropic scan, sub-millimeter. Wow, very high resolution, ultra high resolution, right? Then I put to the same scanner, I'm making a, of course, like cartoon case out of it. And I put a, let's say, gray mouse lemur. And I had 0.8 millimeter fMRI voxels as well. Would this be really impressive for you? Like you would say ultra high resolution, super result? You wouldn't, right? Why? Why you wouldn't say it? Well, because the brain itself is smaller. So to resolve the same amount of information in their cortex, you need smaller voxels in a simple way of speaking, assuming that the volume kind of scales in a way linearly across in terms of cortical thickness. But anyway, my point is that, and this is a struggle. Like when I look at the animal literature, I am mostly a human researcher, but they say their relative resolution numbers, but I struggle to find their cortical thickness. And when I find it, I need to divide it with the resolution and see how close am I in humans to that, you know? I think we should really by default use this relative resolution. And maybe it's not the right time, but I might want to talk about it next year or maybe after some discussions with others. Let's define what it is. Let's define. One way of defining, and this is turning the verbal formalism into like an equation one. We always said, oh, we have 3 millimeter thickness, right? More or less. I have 1 millimeter layers. I can put 3 layers inside, or sorry, like 3 boxes inside. Yeah, so maybe just, I don't know, divide 1 by 3 or something. of course, this doesn't really consider what would happen if your cube is rotated and you are sampling the curved cortex in a not like a perfectly fitted way. But maybe we can think how to like tweak it. But this would be one way of thinking about the relative resolution. Like let's use number one, like you have to measure your cortical thickness. You have to report your cortical thickness across species, across areas, whatever. You of course, I hope know your fMRI resolution or MRI resolution and report something together with these two numbers, you know, per ROI, per subject, per lobe, whatever, per species, so that we can see how much we are actually resolving and not get confused by these claims of, oh, like microliter, less than a whatever liter. Okay, but this is something to maybe formalize a bit further in the future. I don't see it like fully resolved now. Okay. So now let's talk about a way of computing equivolume geometric layers or equivolume normalized cortical depths. So rule number one, if you want to implement some equivolume algorithm yourself or do hand calculations or whatever, what does it really require you to really define this? So, well, the first thing you need to do is to define a unit volume, because you can only take like a pieces of a volume and keep it equal if it is curving and whatever, it can be different shapes, by first defining that unit volume, right? If you have just like a line-wise measure, there's no volume there. It will just be your equidistant measurement. Therefore, we need to find a way of talking about these unit volumes. And as an example here, I just plotted these three unit volumes, arbitrarily defined here, you know, don't take it as too formal. It can look like this in the gyrus, it can look like that in the very curved sulcus, and looks like very rectangular and straight in a wall. And now, the next thing you need to do in your algorithm is to somehow compute curvature. So you defined your volume, unit volume. Actually, people, I mean, I shouldn't say people statements, but like there is a common way of computing curvature in MRI data processing, and that's called a fitting and osculating sphere to a triangular mesh to compute the curvature. And that is really like, is something you can do very nicely in a triangular mesh data structure. But there are other ways of computing curvature in a discrete domain. And one way of computing curvature in a discrete domain, and curvature just means a measure of how much a shape bends. Like how much a shape bends is called curvature. And there are different ways of measuring this concept, right? One concept that actually we made up during developing Laney is that, okay, we define these unit volumes. Then on the way going there, you need to compute equidistant cortical depths anyway, like cortical depth divided by thickness. So this gives you a nice, like a two-category division of your local area, like below the middle, equidistant-wise middle of the gray matter, or Van Essen calls it mid-thickness. He warned me, actually. And the upper part is like the outer part, okay? And now, let's think of a wall where we don't have a curvature. So these two volumes, sub-volumes of this unit volume will be equal. And if you plug it in the following formula, that is, let's say this is 10 volumes of units, whatever. This is 10, so this is 10 divided by 20 will be 0.5. Okay, what happens if it is a gyrus? Which means that the inner part, the half of the cortical thickness closer to white matter, will be in volume smaller than the upper part. This is what it means for like a 3D shape to bend. And that will give you a different answer. So this will go to a lower number, this like actually approach to 0. And in a sulcus, it's the other way around. It will approach to 1. So this is a nice constraint regime that you can compute your curvature from 0 to 1. 0.5 tells you that this is straight. One way of doing it. I'm not saying this is the best way, whatever, we can have that discussion another time with like software developers. But the point here is that this regime is quite nice and natural to do ternarization or other like higher number of categories, categorization of this continuous domain. Basically, like, the simplest thing you can do is that you can separate your cortex into a wall, straight, more or less, the really curved, like a gyrus, and the other types of curved sulcus part. And I think many of you do have a look at fMRI activity on flat surfaces and whatnot using this light gray, dark gray underlay that tells you, oh, where's the sulcus, where's the gyrus, right? So that's important, but that's a binary classification. Whereas in this domain that we are seeing now, it is very important to have, I mean, if you are going to categorize a continuous curvature measurement, you need to have at least 3, because layers behave very differently at 3 regimes, at the walls, gyrus, and sulcus. So it has to be at least 3. So we need to get used to this at least 3 bins categorization of the cortical curvature, you know, dark for the really sulcus, maybe a bit less dark for the walls, and so forth. I think you did get the point. So one example of, I mean, this is not a new idea. This is not an idea that came from me. And actually, if you had a chance to talk with David Van Essen, he will talk about this for like half an hour, because he keeps complaining that people arbitrarily put this binary curvature on top, which curvature should be like a continuous measurement and so forth. Okay, one way that I dealt with it in the past, before I knew about equilibrium principle or any of these things, was to basically, so we had this diffusion layer MRI study. I mean, details are not important, but we had a whole brain segmentation. We computed the curvature using triangular meshes like free surfer wave, brain Boger wave, whatever. But instead of 2 bins, we created 3 bins. And there we called sulcal fundi, straight walls, and gyral crowns. This is a bit of a mouthful because someone did corrected me to not say just sulcus and walls and gyrus. It's a bit like, this field is a bit too pedantic sometimes in an unuseful way. But what happens is that my point here is, like, just binning your curvatures and looking at your layer profiles across these 3 curvature bins can tell you already an interesting story about what you see in your fMRI activity, diffusion MRI activity, or anatomical activity, and whatnot. And just to note that in this paper we didn't use equivolume principle, so that was a wrong part, but it was low resolution anyway. But for instance, have a look here. I mean, it doesn't matter, it's 3T70. Just have a look at the superficial part here, gyral crowns, right? And then compare it to here, sulcal fundi. And the brightness of the voxels are like how many voxels were fitting into that bin of the fibers angle with regards to the surface. So I was trying to measure how angulated the fibers are inserting themselves to the cortex, like to the gyrus, to the sulcus, in a way like similar to what Bok was doing by looking at it at the microscope. But of course, it's not a microscope. But anyway, that's not the part. But the point is that what they say, what the data says is slightly different. For instance, here it's like really bright there, but here, like that brightness more diffuse. This is one way of like understanding what your curvature is telling you, and maybe how you might exploit this further. Because also, going back to the relative resolution point, yes, if we are at a wall, and if we align our imaging in such a way that we fit 3 voxels inside of a 3 millimeter cortical thickness, yes, we can have like 3 things, fine. But if we are at a really curved gyrus, the deep layer becomes very thick, right? So all of a sudden, our relative resolution with our fMRI data for the deep layers actually increase if we are at a gyrus. And similarly, if we are at a sulcus, because of the geometric constraint, the superficial layers increase in their thickness. So our relative resolution for the superficial layers with the same 0.8 millimeter, 0.1 millimeter, whatever, fMRI data increase in the sulcus, right? So maybe there is a meaningful way if we combine them in the right way. And this is a speculation. I didn't do it. It's just like what I think that should help, maybe, you know, and of course we need to be careful, but maybe by like pooling data carefully in the right way from exploiting the curvature of the human cortex, right? Not treating it as a noise, but understanding it and fully exploiting it. We can realize that actually we have more than what we thought we have. It only required us to change our mind's eye, like consider the curvature in its true extent in 3D. So maybe this is some interesting analysis that some of you might be interested to do in the future. Okay, so now going back to giving you a little bit of intuition and another point of confusion that I would like to fix in this lecture. So let's think of the ball brain again. And now let's measure infinitely many amount of layers, or I would prefer to say it's just a layering metric. It's just a measurement, infinitely precise. And this would be how the metric changes over space if you do equidistant measurement. This actually boils down to Euclidean distance. If you go to equi-area, and I mean, we can discuss how this comes about later, it's not so complicated, but it goes to the square of this normalized equidistant metric. So which means that if I impose arbitrary number of layers on this, they will automatically be equally area. And if you have a volume and a really curved cortex, like a ball basically, cannot be more curved, I mean with some constraint, then it will go to the third power, this 0 to 1 thickness normalized measurement metric. And I say 0 to 1 because your cortical depth can never go above cortical thickness. If it goes above, something is wrong in your computation. By definition, it should not go above. Okay, now I will give you the example to give you a bit of intuition. So I had started from this smooth metric, a bit maybe mathematical way of thinking about these distances and stuff. Now I impose two categories on it. And this is what I get. And look how surprising, right? Like this white stuff. When you think of a ball in 3D, of course, we look at a 2D slice of it here. It looks really thin, but if you really comprehend the ball in 3D, the white stuff here has the same amount of volume as the gray stuff in the middle. Now let's say we look at 3 layers, 4, 5, 6, 7, and so on. So my point here is that if you are looking at a really curved piece of the cortex, and if you computed many layers there, whatever, like you upsampled your data, or you have postmortem data, right? 100 micron, 50 micron, chunk of a brain. And you really would put the equivolume principle in action, and you happen to look at a very curved region of the cortex. You might end up thinking that, oh, but this is too thin, like something is wrong, like what did go, no, like it's the right way, you just didn't get it, you know, Plateau scale. Okay, now let's move towards a bit more practical part. I will try to squeeze some practical like notes here. And one issue, and this will be a standing issue at the end. Let's assume that we divided our cortical geometry into unit columns to begin with, right? And then we put the equivolume principle in action. If you do it really strictly, what happens is the following. In this pizza chunk, you have equally volumed layers. In that pizza chunk, you do have it, but then it becomes straight. I mean, this is a toy example, but just to make my point. And all of a sudden, you have this jump in between. But in the biological tissues, we do not have such jumps. Not so straight. So there is some smoothness constraint there. Therefore, anyone computing the equivolume principle, based on how they define the unit volume or unit column, sometimes we refer to, need to somehow put some smoothing constraint, some special regularization into the computation. And this is just a cartoon example, not exactly how the algorithm works, but this is what we do in Laney. We have a parameter called like smoothing, something smoothing. It's written in the help menu. I don't remember actually. And basically by tweaking that parameter, you can enforce more regularization or less. And we made it a free parameter because we do not know what is the right amount of smooth regularization right now. We need to investigate RNG architecture, site architecture, Milo architecture. We need to empirically derive this smoothing parameter. This is an open question, you know, that we need to use postmortem, different species, maybe in vivo, but we don't know. We just tweak it in a way that it looks nice to our eyes. But that's an open problem. Now, getting a bit more practical and useful for a user. For instance, here what you see is that you give a segmentation to Laney. Laney doesn't segment, by the way, to correct that. Laney makes use of a segmentation. And in this way, you can see that there are actually 3 types of tissues: the gray matter, pure gray matter, let's say, the outer gray matter boundary, and the inner gray matter boundary. You give these, like you label your voxels in this way, and it only requires voxels, not triangular meshes. You give it to Laney, it gives out by default at least like these 2 outputs. That is the metric file and the layers file. If it was just up to me, I would just give you the metric file as an output, because you need to understand that this is an arbitrary binarization that you are imposing on your metric. But because of the historical reasons and as requested by Renzo Huber, I agreed that I give by default some number of layers. It's the automatic binarization or categorization of the smooth metric. And you can activate the equivolume flag to get the equivolume versions of these metrics. And it would look like this, basically. You see that there's a nice symmetry in this beautiful, like a geometric case, how the deep layers shift up in thickness in the gyrus. Let's say this is white matter here. And the superficial layers shift down and become thicker in the sulcus. I hope you really like see the intuition behind it without like even thinking too much about it. Now let's apply Laney's algorithm. I mean, I also would like to say that this principle, like implement it in your own way. I don't care. You don't need to use Laney. You know, that's a natural principle. Implement it in however the way you want. But what you should check is the validation with regards to really high-res data. And this is one data set that is from Ding et al. 2016. I believe this is a T2 star weighted image at 200 micron isotropic resolution and the post-mortem image. And you can see that there is this like middle layer, mid thickness, whatever, like darkness there. If you have the equidistant middle layer, you will see the yellow line. If you have the equivolume middle layer, you will see the green line. And see how natural the green line fits to what is in your data empirically. And we didn't even make use of this anatomical contrast, right? We computed purely based on geometric principles. So this is why you should care about the equivolume principle in like really high-res data. And there is a nuance point there. We struggle sometimes a bit with Renzo because of a blog post that we write a couple of years ago. Equivolume principle might not matter today if you have 1 millimeter data point, 8 millimeter data. Because as Renzo showed in his lecture, we are at the edge of starting seeing these layers, right? But in the future, when we have 0.35 millimeter, 0.1 millimeter and higher, not even fMRI, maybe post-mortem and histology as well, like big brain data set, we cannot do without equivolume layer principle. This is an example on the big brain data set. Just to say that, hey, like, I don't know, I thought this might be impressive, like 100 micron whole brain data set, we can put the segmentation in Laney and in like 10 minutes or 20 minutes at the 100 micron isotropic resolution without like really optimizing the hell out of the C code. We get the equivolume layers and equidistant layers and so forth. Okay, now to convince you even further, if you are not convinced, and if you are type of a person that is only convinced by indirect like measurements of the phenomenon, let's plot our layer profile using equidistant and equivolume principle in action. However, let's not use fMRI data. Let's use anatomical data recorded at 0.2 millimeter isotropic resolution. And let's not use functional activity. Let's use T2 star weighted values that comes out of the scanner, like where we really see those layers, right? So now look at this. Equivolume, equidistant. Equivolume, equidistant. What's different? Can you see? What about this, let's say T2 star weighted signal dip? In the middle layer, yes. Here, if we use equivolume principle, it is in the middle, it's in the mid layer. If we use equidistant, it is below. And that region is much more varied. Look, we are sucking up some variance, right? Why? Because we are putting the right reference frame on top of our data. This is in a way similar to using rotating reference frame to talk about T2 star weighted signal. In a way, that's the same idea. And maybe with further tweaks in the future, we can suck up even more variance. Maybe there's like some other principles, right? On top of equivolume, maybe other geometric constraints that we can plug in and make this even tighter and tighter fit. And that would be histonomy. That's what Bock is talking about, right? Using the numbers first, your right reference frame, looking at your variance in the right way. Okay, so this is the, to be even more practical, without spending too much time. If you want to plot what I am plotting here, this is a layer profile scatter plot. And by the way, like we don't agree on one way of plotting something ever with Renzo. We have like 10 different ways of plotting layer profiles and whatever. You know, you choose your own way. But the way I like is talked about in the following YouTube videos. You can watch it at your own pace. And basically it will teach you how to come to this scatter plot layer profiles. And notice some details here that you must write. Of course, the y-axis units, but on the x-axis units, you must write your preferred pedantic correct terminology here. Last year I used normalized cortical depth and indicated equidistance somewhere in the title. Actually, I forgot to, I cropped it out, but like I should have done the equivolume normalized cortical depth, right? Because that matters. One has to know, like you have to state that if you show layer profiles. How did you compute your layers? How did you compute your cortical depths? Okay, maybe if you have too much like data, if you are one of those lucky people acquiring images at 100 micron, looking at chunks of the brain, maybe consider using 2D histograms, like first scatter plot, or it's too dense, I cannot see the variation. Switch to a 2D histogram. At the last step, to convince your reviewers to make it easy for them to swallow whatever you are showing, maybe then consider switching to a line plot. And of course, I didn't do it here for simplicity, but you should add your error bars on top. Because as you progress from scatter plot to 2D histogram to line plot, you are compressing more, but you are also losing the variance. So maybe like being aware of that, oh, there are these big outliers here and there, and like this might be something to actually report in your scientific results. So now going beyond layer profiles, and this is something that I got inspired by one of John's papers, and I really put it into use vigilantly, I would say. And this is from one of my recent papers, the usual suspects, of course, Saskia and Renzo there. We need to go beyond just cortical layers, cortical depths. And what do I mean by that? Due to the segmentation differences, due to using different software, due to having different biases, maybe someone puts the superficial, like a boundary of the gray matter a bit too much into the CSF or too little, whatever. It's important to plot your data that goes beyond your cortex, okay? And I think the right way of doing it is that for the middle part, so let's have a look at this. This says gray matter, right? 0 to 1. It says equivolume depth. It's a 2D histogram. There is some quantity plotted there. But here, what do I do in the right and the left part of this 2D histogram? There are actually two other 2D histograms here. This is a three 2D histogram composited into one. And these are the seams that you see. And why? Because in the middle, in the cortex, we have this normalized cortical depth, normalized layers, right? But when we go beyond the cortex, above, the right unit of measurement, the right reference frame is not a normalized one. We don't know how to normalize it. Therefore, we should revert back to physical units of measurement. And we should measure the voxels distances as a function of millimeter, and then plot that one as a separate 2D histogram, scatter plot, whatever, together with our cortical layer profile, so that we can see what's going beyond just above our gray matter, right? Maybe you are at an ROI that is small, but there's a very big vein on top in one of the subjects. If you would have plotted this, you would see immediately like a huge activity the moment you go above your cortical layers, right? And then maybe you say, wait, let me go back and check. Maybe this is a big vein here. and similar in the white matter. So there are ways of doing it. In Laney, we have 3 programs, LN2 layers, LN2 borderize as a utility, and LN2 geodistances that compute the geodesic distance in 3D voxel space. Okay, I'm good on time. So now, a side note for those who are more into development and for the future. So the ways of implementing the equivolume principle, the ways before we implemented in Laney used triangular meshes, these free surfaces, brain-Voyager surfaces, those things, you know, that you all work with, and Dog yesterday talked about it. So that's a choice of data representation. It's not a monolith that we have to pray to and obey. Someone decided that the best way of representing cortex is using maybe triangular meshes, not the voxels, and therefore they went ahead and put actually a Lagrangian worldview into the data. What do I mean by that? When you trace like points in space where they move, and also going back to the distortion correction talk, I remember that there was a distortion correction that was proposed to be done on the surface, right? And the benefit was, yeah, you just move the points in space. So if you have those things, those points in space, you are moving them without really, you know, like resampling them. That's like a Lagrangian worldview. And there's the Eulerian one, which is you move those data points in a grid, in a regularly spaced lattice. And that's our voxel space. I mean, maybe we can discuss further. There is like some thoughts on it in general, but these are 2 different ways of representing your data with different advantages and disadvantages for computing different quantities. And actually, if you look at the particle simulations field, computer graphics, for instance, maybe most of you watched Frozen, right? There's a snow animation there, snow simulation. They use a simulation called semi-Lagrangian, which means that some parts that they compute to move the snow around is Lagrangian grid, voxels. Some part is, like Eulerian. Other parts are Lagrangian. They convert it into like points in space, move them, compute different things. And they have different like computer, like a software design advantages. And what I'm trying to say is that sometimes we get the comment with Renzo that, oh, you are operating in the voxels. This is the wrong way of doing it. You need to use meshes and so forth. No, this is just a subjective decision of some developer. You know, they thought triangular meshes were more fit to compute stuff. We like voxels. We find it more natural to work, especially at really high-res data. Anyway, maybe this was a bit of a tangent. So how many layers should I have analyze, extract? I would say that you need to think about your nominal and effective resolution to like answer that question. Like you have 0.8 millimeter voxels, but actually you have a lot of points spread, and effectively you have 1 millimeter and so forth. You need to think about the cortical thickness in your area and relative laminar resolution, which means that you need to think about the curvature and relative laminar resolution to exploit your relative laminar resolution to its fullest. And this is just an example from Laney to say that, hey, you have anatomy, you have a segmentation. We can give you very easily by enabling the thickness and curvature flags in the voxel space directly, the thickness and the curvature measurements continuous. And you can binarize them in the however way you want. So now takeaways, but there will be like a final 10-minute part that Renzo wanted me to put. So this is not the end of my talk. So maybe take a picture here. I would say that if you are going to do layer fMRI, you must read these things. Okay, I really want to emphasize it. You must read Bok. I would say he is the founding father of our layeronomy field, maybe. Layer histonomy, these chapters. And then I would really highlight that you should have a look at this book by Geyer and Bob Turner called Microstructural Parcellation of the Human Cerebral Cortex. This will give you a very like a satisfactory outlook and big picture with regards to the history and what people were doing at the beginning of the 20th century and how they were delineating layers and so forth. If you are interested in algorithm development, take a note of these papers, because these papers are the ones that I know that talk about equivolume principle, the different ways of implementing it. Okay, takeaways 2. I would say true layers discussion is superfluous. We need to move towards histonomy. Let's stop talking about who measures the true layers. I find it like really unuseful and unproductive. That's my personal opinion. Right now, it might change. Please keep in mind the areal thickness and curvature are critical for relative laminar resolution. I think this point I emphasized many times. Okay, blah, blah, blah. What do I write? Maybe have a look at the gyrus sulcus walls separately. And please scatter plot your data first to understand the true variance in your layer profiles and maybe some errors there. Line plots will hide. So highlight, don't hide. Remembering Paul Taylor from AFNI team. And what do I say? Look at the anatomical layer profiles as well. Hey, like don't just plot your beta values or t-scores and whatever. Like look at your T2 star weighted signal. If you have high-res anatomy, plot that, you know, that's useful. Oh, and the cortical depth point. I think I talked enough about it. Okay, so last 10 minutes. So this is something that I talk about as the request of Renzo, and I highlight that this is a speculative, like a train of thought, and I hope to generate some discussion, conversation later, maybe with those of you who are more statistically minded. And I call it laminar spatial hypothesis testing because unfortunately spatial GLM term is taken. That's very general, right? Spatial GLM can mean many things. Those Nijmegen people. I'm just joking. Okay, so now first remember this thing. Okay, I will try to establish an argument in 10 minutes. So this is a voxel. This is your time series signal. You have time. You have equal steps in time that you sampled your data. fMRI signal, you know, it goes from 100 to 102, 2% signal change. Oh, nice, you know, activity. So what do we analyze? Like, how do we analyze this data? We fit a model. So we basically know, I mean, I think most of you must know about this. So we have the MRI data. We provide some vector. That's our design matrix determined by the user. And the GLM finds the multiplier and the additive term here in this modeling. And we have a residual tells us how good the modeling fit. Okay, fine. Now let's consider the following case. We can do GLM on an ROI as well, right? I think in the past or maybe currently still people do this. They pull together many voxels. They have multiple voxels like contributing to each time point. And you can do modeling just there. There's nothing wrong. Fine. Now think of the following case. You have an ROI. You have the following toy activity that I draw myself. Double peak activity, okay? You are excited to write your like feed-forward feedback theory and whatnot. So now let's consider this ROI. There are voxels inside there, right? For each voxel we know, is this an ROI or not? Yes. So each voxel has a cortical depth. Each voxel has an fMRI activity or the summary of the fMRI activity. So now each voxel's depth, if you use the right metric, will be on your x-axis, going from 0 to 1, white matter to CSF. But notice that this is a gyrus, right? So by definition, we have less samples in the deeper layers because that's what the geometry imposes on us. There are just less voxels there. And notice that data points here are fewer than the data points in the superficial layers. Okay, so this is in a way like similar to our GLM construction, right? But what is different? Well, the difference is the steps on the x-axis. They are now irregularly spaced in space and also irregularly populated. Like how many samples we have in different regimes at this very curved region. Well, you can just do GLM there as well, you know, and these are the points I was highlighting. You can just use GLM, like you can fit a model there. It's just that the data that you fit is a little bit different than your time series signal. And that requires you to indicate a design matrix or a vector that is your spatial laminar hypothesis. That's what we call, maybe it's not the right term, but you expect double peak, right? So you can say 0, 0, 0 here, 1, 1, 1 between the 10% and the 30% of my normalized cortical depth, and 0, 0, 0 again, and 1, 1, 1 at the 60% to 80% of my normalized cortical depth. That's like a way of stating what you expect from the data. You can have different expectations as well. You do the model fit and you see how well it fits to the data. Okay, I'm good on time. So now let's find, but this is at the ROI level. Maybe we want to go beyond ROIs because we have all this high-res data, right? We want to look at maybe much more fine details of our region. Well, how can we do? Let's zoom into our ROI, and now let's think of a small window. And so a window, right? And let's imagine that we can shift that window around. I hope that you can see, right? So the parameters are the size of the window, shape of the window. There are voxels in those windows, and there is activity or anatomical contrast in those windows. And we can also shift them continuously. Think of it like that. They don't need to be mutually exclusive. It's just the way I draw it. So now let's imagine the flat version of this curved cortex. And similarly, you can imagine that you can have windows that are shifting around, right? And in each window, you can conduct a GLM, like a modeling, right? You can have a model, your laminar spatial hypothesis, you fit it, and you see how well it fits there. Then you can convert your thinking, what you think will happen in the cortex, into a number. And for instance, if you have a double-peaked model, it will fit well here, but not there, right? This might be one way of doing, like doing this histonomy thing, like trying to move beyond just looking at, oh, my activity is double-peaked, this and no, like really try to numerically analyze it. And now this is the point I think I will try to set up Anna's talk a little bit. And because I was really inspired by her paper, in of course 3D, things are a little bit complicated. We need to flatten things, and in a high resolution regime, we have flattened things and we have depths as well, right? Now we can think of windows moving around in this 3D domain as well. And we can do hypothesis testing there as well. So now one way we did use it actually, and we did publish a paper this year about using this, was to investigate columns, a very simple way of spatial laminar hypothesis. The column hypothesis just says that, hey, within a given, like a cylinder of the cortex, I have the same type of activity or category, activation, whatever. So this is a very simple laminar hypothesis. And basically we can have the cylindrical kernels, move them around in our geometry and see if they fit to this hypothesis or not. And now just to give you some pointers, like that thing, we called it columnarity index. We didn't call it like modeling and so forth. Yeah, okay, I'm done basically. But according to me, it's 1 hour, 12 minutes. So I have 3 more minutes. So you can have the literature examples from here. You can have a look at the programs that we have in Layerification to do this stuff. We can also use those things to smooth layers, our anatomical data. And this thing, because Renzo loves it, we have also something called LN2 columns. Have a look. And the last word, with great power comes great responsibility, right? So if you use these tools in a malicious, nefarious way or ignorant way, you might just end up creating layers out of nothing. And maybe the contrast is not so good in this image, I don't know. But here what I did was I went to this region and I shuffled my voxels. So there is no lamina. But I smoothed so much, using so much layer smoothing, I ended up seeing some layers, right? Be careful about that. Okay, the last part, I'm done. Standing issues, and actually one issue was nicely asked by Daniel in the first day. So first issue, how large should the unit volumes be? We don't know, something to look for using empirical data. Is the geometric constraint enough for enacting the equivalent principle? Should we consider other mechanical forces that might be? And this evidence might come from like a mechanical morphogenesis field that study the development of the cortex. Does the equivalent principle apply to all types of layers? And Daniel asked about this. Does it work for angioarchitectonic layers, myelin, cytoarchitecture? Well, I don't think we know exactly for angioarchitecture. To what degree historical and current cortical parcellations are affected by the lack of equivolume principle? This I don't know. If someone knows, let me know. And what are the neurobiological forces that perturb the full geometric layerification? I think it's similar to the previous one. Oh, let's test.